space, time, and randomness. And we are interested in how things work together, under which conditions we obtain a joint convergence rate. Then in the second part, I will focus on the spatial part, and there more precisely on the form-induced setting. So when we only know our generator via a weak formulation with a given form, and I will present you a spatial convergence result for this case. So let's start with an example. We are looking at the heat equation, but a slightly perturbed heat equation instead of the Laplacian. Here we have the gradient of some coefficients times the gradients with Dirichlet boundary conditions and some initial values. And these coefficients depend on the spatial coordinates and then yield different value from the vector z. And this can be seen as some kind of material constant. So how well is heat conducted through the different layers of our composite material, for example. And this is where randomness enters, because we assume that a priori we don't know how our medium is composited. So which zk is assumed in which area. So we assume that z is the realization of some random variable large z with a known density pz. This is what we want to solve in the following. And we don't want to solve it analytically, but numerically. So let me introduce the function analytic framework for doing so. For the spatial coordinates, we are working in some Hilbert space H, which we assume to be separable. And then for each z in Rn, we assume that we have a closed operator AZ, such that outside of a null set, minus AZ generates a contractive semigroup Tz of T. To take the random setting into account, we now pass on to the space which I denote by bold H, which maps Z to an H valued to a value in H. So we have L2 of Rn weighted with a density with values in H. And we can actually look at the corresponding multiplication operators if we assume measurability for these AZ. And we can also look at the corresponding multiplication semigroup, which we denote by bold T of T. And then it turns out that
Hello, Katharina.
Yes, hello.
I think your speaker is off. Am I right?
Do you hear me?
Because I cannot hear you.
I can hear you very well.
Okay, can anybody else not hear me?
Right? I cannot hear you. I cannot hear anything.
Okay, I think apart from Isan, everybody hears me, so I'll just continue giving my talk, and if somebody else does not hear
I don't know what happened.
Please write in the chat.
I'm the only one that has this problem. Anyone else? Okay, yeah, continue.
I just continue.
Sorry.
So, yeah, this is the functional analytic setting we're working in, and we now want to approximate. So we want to approximate the solutions of the abstract Cauchy problem associated to the generator bold H. And we do so by discretizing in space, so everything related to H, in time, and in randomness. So let's quickly recall how that is done from a functional analytic point of view. In space, we choose some space discretization scheme, which means choosing an approximating sequence of Hilbert spaces Hm, and for each z in Rn, operators AZm. Of course, how exactly you choose them depends on whether you use finite differences or finite elements or another space discretization scheme, but they should be chosen in such a way that, again, outside of a null set, minus AZm generates contractive semigroups. And again, we can look at the corresponding bold spaces, so Hm is L2 of Rn weighted with Pz with values in Hm, and add the corresponding multiplication operators and add the corresponding multiplication semigroup Tm of T, which then yields our approximate solution in space. Of course, our initial datum is not a priori in these spaces, so we need to project down. So let Pm just be the orthogonal projection here. And correspondingly, we have a bold Pm between bold H and bold Hm. And if we do so, we obtain a spatially discretized solution, now mapping to Hm as a subset of H by just applying the approximating semigroups on the whole space to the projection of the initial values. Next up is the temporal discretization. Here we perform a chain of approximation in a fixed time interval. So let's say we have some final time t0. And we do so by subsequently applying a consistent time discretization scheme, bold Fm, which maps between the same spaces as the approximating semigroups Tm. And successively, I mean that we apply it nk times. We allow for different time steps. So we have a vector tau k of time steps, which yields a grid tau k of the times that we hit with our time steps. And applying this instead of the semigroup yields our discretized solution. For the sake of a short notation, let's denote that by bold F index mk, which just means applying the time discretization scheme successively for each time step until we reach the time at which we want to have a discretization. And we denote the approximate solution we get by umk, where now we only allow for times in tau k instead of the whole of 0 infinity. The last step is the polynomial chaos expansion to approximate the randomness. Don't worry if you haven't heard about that yet. If you look at the right spaces, it's nothing else than an orthogonal projection. Because what we want to have is, instead of any L2 dependence on Z, we want to have a polynomial dependence on Z of degree at most n. And this is equivalent to truncating the generalized Fourier series after the terms corresponding to the first n orders, where we choose orthogonal polynomials as the orthogonal basis, which correspond to this probability density Pz. Again, it's not sufficient to do it scalar valued, but we have to do it vector valued, but this is not a problem because our space H is assumed to be separable, so we can just have a series expansion and then apply the scalar polynomial case expansion, scalar PCE, just to every factor of it. And finally, we obtain a fully discretized solution umkn by just applying the vector valued PCE to the temporally and spatially discretized solution, so that for each time step in the grid, we get a function which is polynomial with respect to Z and assumes its values in Hm. So this is the setting I would like you to keep in mind. And now we also need a notion of how fast something converges. So we want to quantify things, which we can do by a rate of convergence. The concept is essentially the same in space, time, and randomness. So let's take a closer look at spatial convergence rates. Of course, we can't assume to obtain a higher convergence rate on the whole space. So we have to input more regularity. So assume we have some space Yx densely embedding into H. And then if the initial datum is sufficiently regular, then we say that UM is convergent of a certain order Px if the spatial discretization error can be bounded by a constant times the stronger norm of the initial datum times n to the minus Px. And this should hold locally uniformly in time. Similar principle holds in time, where we just have m replaced by the maximal time step and assume the maximal time step to be uniformly bounded, which doesn't pose a problem because we only want to look at a finite time interval anyways. And a similar problem in randomness, so that we obtain the spaces Ym for the temporal convergence rate and YZ for the randomness convergence rate. So for example, if we look at the previous problem, we have the abstract Cauchy problem with the gradient of AZ times the gradient as the generator on H2 intersected with H01. And we could, for example, perform a finite element method with, say, quadratic triangular elements. This is known to have convergence rate of 3, given that the initial datum is sufficiently smooth. I'll come back to that in the second part of my talk, so please allow me to be vague for the moment and say sufficiently smooth. In time, the two standard approximation methods are implicit Euler and explicit Euler, which both have a convergence rate of 1. But of course, you could also take a higher order method such as Crank-Nicholson here. And for the polynomial case expansion, we can choose the order after which we truncate. So let's say we look at the polynomial case expansion of order n equals to 4, which yields a convergence rate of 4. And now we want to know when we can combine them. And indeed, there are some further conditions necessary, because just because every separate discretization converges of a certain rate, this just doesn't necessarily mean that they work well together. So let's say we have the spaces for the separate convergence rates I just introduced, and assume that the space discretization and the randomness discretization converge with the respective orders on the respective spaces, so L2 with values in Yx or Yz tensor H respectively. Same for time, but because we have a different time discretization for each m, we ask them to converge uniformly with rate pt on the respective space. So these are the conditions that, of course, we need. We can't expect to have a joint convergence rate if we don't even have them separately. And now I have two conditions so that they work well together. The first ensures that space and time discretization match each other, and we require the projection, so the orthogonal projection from H to Hm, to be uniformly bounded if considered as operators mapping into the space on which we have a temporal discretization rate and on some space. So it doesn't have to be uniformly bounded on the whole of H, but we can choose another space continuously embedding into H here. And the second condition ensures that the randomness discretization works well with the other two, because we ask the temporal discretization schemes Fmk to be uniformly bounded for all times k and n, if considered as mappings from Yz tensor Hm, where Yz is the space on which we have a randomness discretization rate, into itself. And for notation, we denote by Y the intersection of the spaces Yx and Yt equipped with the maximum norm, and assume they also embed continuously into H. And if these two obvious and two real conditions are met, then we actually obtain convergence of the fully discretized solution with the rates one would expect. So Px in space, Pt in time, and Pz in randomness, given that the initial datum is in Yz with respect to randomness and in Y with respect to the spatial coordinates. Unfortunately, I won't have the time to prove that for you, but let's quickly take a look back at the example. So if we choose implicit Euler, then all conditions are met from the previous theorem, and we indeed obtain a joint convergence rate of 3, 1, and 4 when using the implicit Euler. One obtains a slightly different picture if we work with explicit Euler. So for example, if we take our time step too large, the condition I mentioned beforehand does not hold, so the PM is not uniformly bounded as a mapping from Yt to Ytm for any Yt, so the solution actually does not converge. But if we choose the time step small enough such that a CFL condition is met, we again obtain convergence rate 3, 1, and 4. So yes, that's been the first part. Let's focus on the spatial direction. And we want to consider the rather common situation that we actually don't have an explicit formula for our generator A, but rather know it via a weak formulation. So if tested with some test function, AU is given by a form small a of UV. Let's make this a bit more precise, this setting. So we assume that the form is defined on another Hilbert space V, which densely embeds, which continuously embeds with dense range into H. And let's assume that the form A is bounded and coercive. Then, of course, we have two tasks. We need to construct a semigroup from that, and we have to approximate that. And of course, one approximates A, so the generator A, by approximating the form A. And a common approach is to approximate the form by approximating these function spaces here. So the standard finite element approach. So we choose a sequence of an approximating sequence of spaces Vm, meaning that each Vm is a subspace, and for any element of V, the distance to the approximating spaces tends to 0 as m tends to infinity. And then we just obtain our approximating forms by restricting A to Vm times Vm. So next task is to construct a generator. For that, we first need an isomorphism, which I denote by curly A, mapping from V into its anti-dual via AU equals the form with only U given as the first input parameter. And it turns out that the right way to associate a generator with that is by restricting this curly A to the pre-image of H under it. This yields an unbounded operator on the domain of all U in V, such that curly AU is an H, equipped with a norm of H. And given that A is indeed bounded and coercive, this generates, well, minus A generates a semigroup T of T. We proceed likewise for the approximating forms, where we have to introduce the spaces HM, which are just the closure of Vm in the H norm. This works both for the infinite and the finite dimensional case, although of course in practice one usually prefers the finite dimensional case. And in the finite dimensional case, HM is actually the same as Vm, just equipped with the H norm instead of the V norm. So yes, this is the setting I would like to keep you in mind. And let's take a look back at the example. Because we don't care about the random coefficients in the second part, let's assume we just have the Laplacian as the generator. The corresponding form would then be the gradient of U times the gradient of V complex conjugated integrated over our domain. And the right function space is H01, because we still assume to have Dirichlet boundary conditions. As you all know, this generates the heat semigroup. So we want to approximate the heat semigroup. Of course, we also need some initial datum, which I will denote by F in the following. And as you saw in the first part here, we need to assume more regularity, which in this case means assuming that F is in the domain of the alpha plus first fractional power of the generator for some positive alpha. And of course, we need an approximating space Vn. And that can be done by any finite element space. Let's take the quasi-uniform finite element space of quadratic triangular elements. So on each of these small triangles you see, we will approximate by a quadratic polynomial. And of course, they should depend on m. So the circumference of each triangle should be at most 2 over m. And to make things a bit more interesting, we can also work not on the whole unit square, but on the whole unit square apart from some domain. Unfortunately, this Dauphin does not work because it's not convex, but as soon as G is convex, Lipschitz and bounded, this works. And we're now interested in convergence rates for this solution. So how well can we approximate our Dauphin? And of course, there are standard results on approximation of semigroups, mainly the Trotter-Kato theorem. There are also quantified versions of that, for example, due to Kappel and Ito. But there, the conditions are always directly.
Sorry, you have 5 minutes. Okay.
Okay.
Thank you.
Yeah. And we want to have the conditions directly on A and on Vm. So not on the generator, but on the form and the approximating spaces. And to show you my final result, I need to introduce a new notion first. This is a certain space parameter due to Aaron, Chalandar, and Amar. And I prefer to look at it via this inequality. So we say that the distance in V of some sufficiently regular U to the approximating spaces is bounded by AU in the norm of this stronger space. And the smallest such constant is what we denote by gamma m of x, where x is some space continuously embedding into the antidual. And by sufficiently regular, I mean that it's in the pre-image of x under H. So to say, how well do my approximating spaces perform with respect to this particular form A and this space X? Likewise, we define gamma m star for the adjoint. And it turns out that the relevant quantities are the decay rates of these parameters. So let's say that gamma m decays with rate p1 if this inequality holds, and likewise for the adjoint. So here's the promised convergence result. We assume that A is bounded, symmetric, and coercive. We can actually do without symmetry, then we just get a bit worse rates. So for convenience, I decided to include it here, bounded and coercive are needed. The counterpart to the projection PM is the canonical injection, which we denote by JM. And we need to assume the convergence, the decay rates of the right spaces. So let's assume that gamma m of the domain of the alpha fractional power decays with a certain rate p1, of course, depending on alpha, and that gamma m star of the whole Hilbert space H decays with rate p2. And if these conditions are met, we actually obtain semigroup convergence in the strong operator topology of rate p1 plus p2, so the sum of these two decay rates, given that we have one order higher regularity, so that D is in the domain of the alpha plus first fractional power. Again, time will not be sufficient for the proof, but let's quickly look at the example. There we obtain P2 as 1 by using, well, of course, we need some knowledge about finite element methods. And one knows that for quadratic triangular elements, you can bound the H1 norm by either a linear decay of the H2 semi-norm or quadratic decay of the H3 semi-norm. So this is where the smoothness comes into play. And we also need elliptic regularity of omega of the Laplacian, meaning that we can control the mixed derivatives by the Laplacian. And combining these two, we obtain P2 equals 1, and also P1 depending on alpha. Then we need another ingredient, which is Carter's conjecture, which is for a large class of domains no longer conjecture, but a theorem, meaning that we can control the H1 norm by the L2 norm of the square root of the Laplacian. And here we really see that it depends on alpha, depending on how much regularity you have. So if alpha is at least 1/2, corresponding to U being an H3, we get P1 equal 2, and otherwise we get P1 equal 1, so that we end up with a convergence rate of 2 or 3, respectively. So yes, that has been my talk. Keep your eyes out on the archive. There will be a paper appearing on that soon. And apart from that, thank you for your attention.